Welcome students to exercise 33, which is about the cardiac cycle and blood pressure and pulse. If you are a CNA, a lot of the blood pressure and pulse stuff will seem very familiar to you, but we're going to start actually with the thing that tends to throw students off the most, which is the cardiac cycle. So when we talk about the cardiac cycle, we're really talking about what happens in the heart during essentially a single heartbeat here. The cardiac cycle graphs that you typically see have kind of lots of moving bits and lots of parts to them that demonstrate all kinds of things going on, both in terms of the electrical activity of the heart, the mechanical events going on in the heart, whether the valves are open and closed, where the blood is flowing. So we're going to look at kind of it in pieces. So you can see this top line here is the ECG. This middle chart is then the pressure changes in, typically they show the left side of the heart, so the left ventricle, the aorta, and the left atrium. If you were to look at the right side of the heart, the volume changes would be pretty similar. The ECG will look pretty similar. The pressure differentials might be a little different because the pulmonary circuit is a much lower pressure circuit than the systemic circuit. The third part here is then the volume going into the atria and the ventricles, and then there's a nice little kind of diagram of where the blood is flowing, what the valves are doing. So let's start with the ECG, since it's the electrical activity that kind of starts off this whole thing. So the P wave is the atria depolarizing, leading to the contraction of the atria. So this is in this early ventricular filling phase. At this point in the cycle, the semilunar valves are closed, but the AV valves are open, and blood is flowing passively from the vena cava and from the pulmonary veins back into both sides of the heart, into both of the atria. Once the atria depolarize and contract, then the last little bit of blood in the atria is kind of pushed into the ventricles, and that's why you'll see the volume of the blood in the ventricles is slowly increasing as the blood kind of passively pools into the ventricles, and then that last little bit gets kind of pushed into the ventricles during atrial contraction. Once the atria contract and push the blood into the ventricles, the last little bit of it, then the ventricles will depolarize, which is our QRS complex here, representing the depolarization of the ventricles. Once the ventricles depolarize, they can start to contract. And so if you look at the pressure in the ventricle here, you'll see the pressure in the ventricle starts to increase. This period in time is part of the kind of systole contraction phase of the heart. But systole in the heart is actually broken into kind of two phases: an isovolumetric contraction phase and then an ejection phase. This portion right here is known as the isovolumetric contraction phase. Iso volume, so same volume. And so if you look at the volume of blood in the ventricles, you'll see it is not changing. Let's look at the pressures here. If we look at the blue line, you'll see as the ventricles start to contract, initially ventricular pressure is lower than atrial pressure, but very soon ventricular pressure will exceed the pressure in the atria. When that happens, that shuts the semilunar valves so that the blood does not flow backwards from the ventricles into the atria. So the ventricles at this point here have now shut. The semilunar valves are still shut, and so the ventricles are closed chambers, blood neither coming into nor leaving the ventricles, and so the volume remains the same, isovolumetric contraction, because the pressure inside the ventricles is still increasing as the ventricles continue to contract. As the ventricles continue to contract, eventually ventricular pressure is going to exceed the pressure in the aorta and the pulmonary trunk. At that point, the semilunar valves are thrown open, and we get one last push in terms of ventricular pressure, and that ejects the blood into the aorta and the pulmonary trunk and out of the heart. So that's this ventricular ejection phase. Once the blood has been pushed out of the heart, the ventricles start to relax. As the ventricles start to relax, ventricular pressure will fall below the pressure in the atria of the aorta and the pulmonary trunk, and the semilunar valves will shut so that, again, blood flows in one direction and does not flow back from those big arteries into the ventricles. This begins the isovolumetric relaxation phase. The AV valves are still shut from when they closed back here. The semilunar valves just shut at this point here, and so we're in another isovolumetric phase where the blood is neither moving into or out of the ventricles. The ventricles will continue to relax and continue to relax and continue to relax until eventually ventricular pressure falls below the atrial pressure, and we're back at the beginning where the semilunar valves are shut, the AV valves are open, and blood is filling the atria and passively filling the ventricles. And we're ready to do it all over again. So the amount of blood that is ejected during each cardiac cycle is known as stroke volume. It is the difference between how much blood the heart can fill with, which is EDV, versus how much blood remains at the end of systole, which is ESV. So stroke volume, the volume of blood pumped by the heart during each cardiac cycle, is the difference between EDV and ESV. EDV, end diastolic volume, the volume of blood in each ventricle at the end of ventricular diastole. So essentially when the heart is relaxed, how much blood can the heart fill with? That's EDV. ESV is the volume of blood remaining in each ventricle after ventricular systole. So after the ventricles have contracted, what little bit of blood remains in the ventricles is then subtracted from what was in the ventricles to kind of begin with. The rest is then that stroke volume, the amount of blood that was pumped by the heart during that particular cardiac cycle. Now, cardiac output is actually the volume of blood pumped by each ventricle in 1 minute. So we take our stroke volume, the volume per cardiac cycle, and we multiply it by our heart rate in beats per minute. That gives us a cardiac output of milliliters per minute. So anything that makes either stroke volume increase or heart rate increase will lead to an increase in cardiac output. So if we increase our blood volume, that would increase our stroke volume, which would increase our cardiac output. If we've got lots of T3 and T4, that increases our metabolic rate, which increases our heart rate, which increases our cardiac output. And cardiac output is one of the things that will affect your blood pressure. The other thing associated with the cardiac cycle are the heart sounds. So it's that typical lub-dub, lub-dub. The first sound is the closure of the AV valves as ventricular pressure exceeds the atrial pressure. The second sound is the closure of the semilunar valves as the ventricular pressure falls below the pressure in the aorta and the pulmonary trunk. So depending on kind of which valve you're looking to really kind of hear, you place your stethoscope either in the second intercostal spaces or in the fifth intercostal spaces, depending on where you're going. So if you're looking at the second intercostal spaces, you're going to hear the closure of the semilunar valves better. If you're in the fifth intercostal spaces, you're going to hear the closure of the AV valves better. Some people have heart murmurs, which are associated with kind of malfunctioning valves. Either the valves will be stenotic, which means too stiff, which means they won't open up all the way, and so you get kind of a high-pitched squealing kind of sound, think kind of like creaky wheels, or they might not close sufficiently because they're weak or insufficient, in which case you get kind of a swishing sound as the blood flows backwards like we don't want it to do. And so they do sound a little bit different than your typical kind of lubbed up, nice healthy heart sounds. Another part of this activity will be the pulse, which is essentially kind of the pounding of the arteries. As your heart contracts and relaxes, blood is ejected from the heart, and then the heart relaxes, blood is ejected from the heart, and then relaxes. That kind of pounds against the walls of the arteries. And so very often we will palpate some of these superficial pulse points as a way of kind of estimating heart rate. And these are kind of some of the most common ones. You've probably taken a radial pulse before. You may have taken a carotid pulse before, but there are a couple of other ones in some of the more superficial arteries. The other half of this chapter deals with blood pressure. And blood pressure is essentially the force of the blood as it is being pushed through the blood vessels. So the blood itself exerts this kind of pressure, this kind of pushing force against the blood vessel walls. We measure it in millimeters of mercury. That's what we always measure blood pressure in. And some of the things that will affect blood pressure are things like your cardiac output, like what we call peripheral resistance, which is kind of what's going on inside the blood vessels, and then also your blood volume. So anything that increases cardiac output, if your heart rate goes up, if your stroke volume goes up, that will lead to an increase in blood pressure. If we increase our resistance, if we make it harder for the blood to flow, either by increasing the viscosity of the blood, increasing the length of the blood vessel, maybe because we're obese, or decreasing the size of the blood vessel radius, the diameter of the blood vessel, making it smaller in terms of its kind of vasodilation or vasoconstriction. All of those will make it harder for the blood to flow. That increases the peripheral resistance, which would then increase your blood pressure. Now, if we were to look at kind of the gradient in terms of our blood pressures in the arteries and veins and capillaries in our kind of circulatory system, you'll see that pressure in the arteries is the highest, particularly in the aorta, and then lowest in the veins, particularly in the vena cava. The arterial pressure is pulsatile. That's what we can palpate superficial pulse points, because the arterial blood pressure rises and falls as the heart contracts and relaxes. So the systolic pressure is the pressure when the heart contracts. The diastolic pressure is then the pressure when the heart relaxes. Typically, sometimes they'll calculate what they call mean arterial pressure, which is an average-ish of the systolic pressure on the diastolic pressure. It's not quite a straight-up kind of simple average, because the heart spends more time relaxing than it does contracting, and so there's a slightly different formula for calculating mean arterial pressure. If we look at pressure in the capillaries, pretty low, maybe 20, 15 millimeters of mercury. That's because those capillaries are really, really thin-walled, and so we don't want them to kind of bust open. So we actually want capillary pressure to be pretty low. And then in the venous system, particularly in the vena cava, you're going to get, almost nil in terms of your pressure. It also does not change with the cardiac cycle like the arterial pressure does, and this really, really low blood pressure is mostly just due to the cumulative effects of all the peripheral resistance and friction, right? The blood has now traveled out to an organ, gone and percolated through that organ, and now it's flowing back to the heart. It's just encountered a lot of wall at that point and encountered a lot of friction, a lot of resistance, and so most of the pressure is just kind of lost. Typically the way that we calculate blood pressure is with an auscultatory method, using a nice little blood pressure cuff or a sphygmomanometer. Essentially what you do is you wrap the cuff around a particular artery, typically the brachial artery, although I've been seeing more and more often in doctors' offices they're going around the radial artery. But you increase the pressure in the cuff until it's greater than the systolic pressure, and then you slowly release the pressure and listen for this, what we call the sounds of cord cough, using a stethoscope. So Typically, systolic pressure is about 120, diastolic pressure is about 80, so 120 over 80 is considered a quote-unquote normal blood pressure. The systolic pressure is what you record when you first start to hear the sounds of chloric cough as blood begins to flow through the artery again after you kind of compressed it. And then the diastolic pressure is when those sounds disappear because it means the artery is now completely constricted and the blood is flowing freely. And that is the end of this particular chapter. Blood pressure is affected by exercise, which makes your heart rate goes up, pain, temperature, even gender can be a role in our blood pressure, and you guys are going to get to play around with a couple different ways of mucking about. Even your posture can mess around with your blood pressure. So in lab, you guys are going to get a chance to not only take some normal blood pressure and pulse measurements, but also kind of muck about with it too and see how your blood pressure changes depending on kind of certain factors.